Okay, in Chapter 8, Section 7, we want to look at exceptions to the octet rule. We're going to find that some structures just don't strictly follow the octet rule, and it's either because it's impossible to follow the rule or it doesn't make sense to follow the rule. And we want to be able to distinguish between those two scenarios. There are three types of ions or molecules that do not follow the octet rule. And those are ions or molecules with an odd number of electrons, ions or molecules with less than a full octet, and ions or molecules with an expanded octet, more than 8 electrons around a given atom. All right, we're going to start by looking at the odd number of electrons. So whenever there are an odd number of electrons, it's simply impossible to arrange the electrons so that every atom has exactly 8 electrons around it. We just can't do it. There's just no way to do it. These types of molecules are called radicals and are typically pretty reactive, unstable, because they have unpaired electrons. One such example is nitric oxide. And here are the two resonance structures for nitric oxide. You'll see that they are not equivalent structures. So here in a bit, when we look at this, we will figure out which one is the dominant structure. That'll be fun. Okay. The second type of exception to the octet rule is when we have fewer than 8 electrons. It's possible to draw Lewis structures for BF3. They give every atom a full octet. And we'll go through the math of how we get this here in just a little bit, but it is possible to draw this so that every atom gets a full octet. However, this structure puts a +1 formal charge on fluorine in a couple of different places here, and it gives a -1 formal charge on the boron atom. Well, fluorine is the most electronegative element on the whole periodic table. If we can avoid putting a positive charge, we definitely will avoid doing that. So because fluorine is so electronegative, it's just not very favorable to put that positive formal charge on the fluorine, especially when it means putting a negative charge on the boron. So we typically will represent BF3 by drawing a different structure, and this ends up being the dominant structure. So there's 4 total resonance structures. One is unique, and it is the dominant structure. And so it doesn't give a full octet to the boron atom, and that's okay. If we can avoid putting that positive charge on fluorine, it's okay that we don't give a full octet to boron. And so if filling the octet of the central atom results in a negative formal charge on that atom and a positive formal charge on the more electronegative outer atom, then just don't fill that octet in the central atom. Now, typically, this is going to happen with atoms that are over on the left side of the periodic table. And you know, a lot of times metals won't do the covalent bonds, but some of them will. So we'll find that typically this happens more with boron, beryllium, and aluminum. Boron and aluminum are in group 3, and beryllium is in group 2. All right, and then our third type of not following the octet rule is when we have an expanded octet. Some molecules are simply impossible to draw without having more than 8 electrons around them. One such example is phosphorus pentafluoride. So phosphorus pentafluoride, there's just no way to draw this so that we can that we don't have at least one atom with more than 8 electrons around it. Now, in order to do this, the central atom has to be in either period 3, 4, 5, or 6 on the periodic table. It can't be in period 2. All right, presumably we're going to be using some unoccupied d orbitals to make some hybrid orbitals, and we're going to talk about this more in chapter 9. And so that's what's going on with this. So when we expand, when we have expanded the octet examples, in some cases we can draw valid Lewis structures without expanding the octet, but we're going to find that those structures may end up being better represented by expanding the octet on the central atom. Again, we have to have in either periods 3 through 6 on the periodic table for this to work. So one such example is the phosphate ion. Phosphate is PO4 3-, and if we go through all the rules that we did, that we've been working on, you will find that that this is the structure you'll come up with, so that everything gets exactly an octet. However, that puts a positive charge on the phosphorus, and it turns out that that phosphorus really doesn't have much of a positive charge. So a better, and furthermore, it turns out that there is some double bond character between phosphorus and oxygen. So it turns out a better way to do this is to draw that double bond, and we will expand the octet between phosphorus and oxygen, or expand the octet on phosphorus. It's in period 3, by the way. And we will have 10 electrons around phosphorus. And that turns out to be okay. Another example of this is with sulfate. Sulfate, you'll see, ends up with a positive 2 charge on the sulfur if we draw it with the normal rules. However, if we share some of these extra electrons in, we can get rid of that positive charge on the sulfur, and we'll end up having 12 electrons around sulfur, but it turns out that's okay. That's okay. If you're wondering what's the maximum number, typically 12. Now, technically 14 may be possible with some weird exceptions, but 12 in this class. We'll just say 12 in this class. Now, before we go and do number 43, we're going to go back and look at SO3 on our in-class assignment. I have that right here. So here is SO3 on the in-class assignment. And you'll notice that we've got a positive 2 charge on the sulfur. Well, it turns out that in addition to that, a better way to draw this is to draw sulfur with 3 double bonds going to 3 oxygens. And that gets rid of the formal positive 2 charge on the sulfur, and it also ends up giving the oxygens a neutral charge. Now, in reality, there is some negative charge on those oxygens, and there's a little bit of positive charge on the sulfur, but it's definitely not a positive 2. So it turns out this is a better structure for sulfur trioxide. All right, so let's look at number 43 on our in-class assignment here. And we're going to go through and do these. So our first thing is, I'm not even going to have the rules up. We're just going to draw our backbone structure first. We're going to count the number of valence electrons. Nitrogen has 5, oxygen has 6, so 5 plus 6 is 11. But we're going to take one away because of the positive charge, so that's going to be 10. So 10. For octet electrons, we would get 8 and 8. So 8 and 8 gives us 16 octet electrons. Okay, and then we will do, and then we are going to do, let's see, 16 minus 10 gives us 6 shared, and that means 3 bonds. So we're going to put a triple bond in there. Now what we want to do is to put the lone pair electrons on, we've got 10 minus 6, that gives us 4 lone pair electrons. So we'll put 2 onto the oxygen and 2 onto the nitrogen. So 2 onto the oxygen. Okay, and so that is our structure. Oh, let's do the one more thing, which is to do the formal charge. So 5 minus 3 bonds minus 2 lone pair electrons. That gives us 0 there. And on the oxygen, 6 minus 3 minus 2. And that gives us a positive 1. So we'll get a positive 1 charge on that. Now, it turns out that there is another structure that we can draw for this. And by the way, in case you're wondering, this is called the nitrosonium ion. It turns out there is another structure that we can draw for this. And that other structure, it just goes with a double bond. It means that we don't get a full octet on nitrogen, but then we avoid putting the positive charge on oxygen. So we end up with a positive 1 charge on the nitrogen. Again, 5 minus 2 minus 2 gives us positive 1. So that's an alternative structure. And it turns out it's a pretty significant structure, right? Pretty significant structure to put the positive charge on the nitrogen. Anyway, this is the one I expect you to come up with. This is just sort of bonus information. All right, now on number 43, the starred structures are exceptions to the octet rule. So this one's going to be an exception. And as soon as we start counting our electrons, that one's also going to be NO. As soon as we start counting the electrons, we see what the problem is. We've got 5 plus 6, that's 11. Well, 11 is not going to work, right? That's an odd number. But let's go ahead and do the math. Octet, 8 and 8. So 8 and 8 is 16. 16 minus 11, that gives us 5. Okay. So instead of 5, we can't have 5 shared electrons. We won't have 2.5 bonds, isn't going to really work. So we're going to cancel out that 5, or not cancel it out. We're going to take that 5 and we're just going to make it a 4, right? So we're going to have fewer electrons. And then 4 divided by 2, that gives us 2. So we're going to have a double bond between the nitrogen and the oxygen. If we look, we've got 7 minus 4, so 7 electron, I'm not 7 minus 4, 11 minus 4, which gives us 7 lone pair electrons remaining. And so there's 2 ways to do this. We can do 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. Now, if you go through and do the formal charge, you'll see that both of these are 0. So we have 0 and 0. But on this one, the formal charge comes out to positive 1 on the oxygen and negative 1 on the nitrogen. Well, if we can avoid having those formal charges, and particularly if we can avoid having a positive charge on the oxygen, that's going to be better. So that is going to be our preferred structure, our dominant structure for this. And this is nitric oxide. Okay, so next we've got NO minus. All right, so we've got NO minus. 5 electrons plus 6, that's 11, but then there's a negative 1 charge, so that's 12. All right, when it comes to octet electrons, 8 and 8 gives us 16. 16 minus 12 gives us 4 shared. That's 2 bonds. So we'll have another bond there. And now we can put the remaining electrons, 1, 2, 3, 4, 5, 6, 7, 8. Right, 12 minus 4 is 8 electrons. So we have those 8. That gives us 12 total. Everything has an octet. If we look, 5 minus 2 bonds minus 4, that's negative 1. So there's a negative on the nitrogen. And oxygen, 6 minus 2 minus 4 is 0. And since the whole thing is negative 1, that makes sense that there is a negative 1 there. This is called the nitrosyl ion. All right, we don't run into it too terribly often, but it does show up occasionally. All right. So now let's look at NO2. Again, our rule is to put the least electronegative element in the middle. So least electronegative element in the middle. Nitrogen's less electronegative than oxygen. So we will have oxygen, nitrogen, oxygen. All right, so nitrogen, oxygen, nitrogen, oxygen. If we count up the electrons, we'll see why it starred. 6 plus 5 plus 6, and there's no charge. So 6 and 6 is 12, plus 5 more is 17. Okay. Octet is 8, 8, and 8. That's 24. 24 minus 17 gives us 7 electrons. We saw how we did this last time. So when you have an odd number, just decrease it by 1. We'll make that 6. 6 divided by 2 gives us 3 bonds. So we're going to put another bond in there. And it doesn't matter which side. That just means we're going to have another resonance structure where it goes the other way. And then 17 minus 6, that gives us 11 electrons remaining. And with 11 electrons remaining, let's just start putting them on the oxygen first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to have 1 unpaired electron on the nitrogen. All right. And clearly we can draw a resonance structure. Let's do formal charge real quick. This one's 0, right? 6 minus 2 minus 4 is 0. And then 5 minus 3 bonds minus 1 non-bonding electron there, and that gives us positive 1. So there's a positive on that nitrogen. And then 6 minus 1 minus 6 gives us negative 1, so there's a negative there. And when we add that all together, that gives us 0, so we're good. We're good. So now let's look at the other structure, which will be oxygen, nitrogen, double bond, oxygen. All right. And let's go ahead and put those formal charges in there. So negative there and a positive on that nitrogen. So this is nitrogen dioxide, and you may or may not remember, but I'm going to go back over here. This is from our Chapter 1 lecture, which seems like a lifetime ago at this point, right? This is from our Chapter 1 lecture, and we saw the reaction where we took a penny and we put it into nitric acid, and we got nitrogen dioxide gas, and that's that brown gas that comes off. Well, that gas is really, really dangerous to breathe. And the reason it's so dangerous to breathe is because it's a free radical. You'll see that there is an unpaired electron on the nitrogen, and that unpaired electron makes it really, really reactive. So we will find that it is extremely reactive because of that radical. All right, so again, that's nitrogen dioxide. So now that we've done that one, before we do N2O, I want you to pause the video and attempt to do this one on your own. I'm going to do it, but pause the video and try to do it. Okay, now that you've had a chance to pause that video and try to do it, let's see if you got the right answer. So N2O, we're going to put our least electronegative element in the middle. And our least electronegative element is still nitrogen. So we'll have nitrogen, nitrogen, oxygen. All right, and count the valence electrons. So 5, 5, and 6. That gives us 16 valence electrons. And for octet electrons, 8, 8, and 8, that's 24. So 24 minus 16 gives us 8 shared. That's 4 bonds. So 4 bonds. Well, with 4 bonds, there's a couple of different ways we could do it. We could do, 2 and 2. All right, and then 16 minus 8 gives us 8 remaining. And so we'll have 1, 2, 3, 4, 5, 6, 7, 8. Another way we could do it would be nitrogen 1, nitrogen bond oxygen. We've seen this kind of thing before. All right, so that's another resonance structure that we could draw. And then here, let's do one more. And that one more, we will have nitrogen, triple bond nitrogen, oxygen. All right. And if we go through and do formal charges, I'm not going to write all the math, but if we do the formal charges, we get a positive 1 here on that central nitrogen, so 5 minus 4. 5 minus 2 minus 4 gives us negative 1 here, and then neutral on that oxygen. All right, here, this one gives us a negative 2 on that nitrogen, a positive 1 on this nitrogen, and a positive 1 on that oxygen. And then this one gives us 0, positive 1 on nitrogen, and negative 1 on oxygen. And if you were going to pick which one, well, which one is the worst? Well, this one is the worst because it puts a negative 2 and a positive 1. It has more charges. So there's more charges there. And this one is not bad because it puts the negative charge on the nitrogen, but this one is going to be our best. So that would be our dominant structure. So that would be our dominant structure because it puts the negative charge onto the oxygen. All right, and then this is called nitrous oxide. And in case you're wondering, that is also the same stuff that is laughing gas. So that is laughing gas. Yeah, be careful with that. If you're thinking of making some laughing gas, you probably should, you should probably make some better decisions there. All right, we've already seen the structure for this, but we saw this in the presentation a little bit ago. So B, F, F, F. So B, F, F, F. All right, and so 7, 7, 7, and 3, that gives us 24. 8, 8, 8, and 8 gives us 32. 32 minus 24 is 8, and that's 4 bonds. And we already saw that we had this, right? We put that extra thing in there, and we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 24 minus 8 is 16 electrons. So with that's our structure. And we even saw that we got a positive 1 formal charge on the fluorine and a negative 1 formal charge on the boron. And that was just not our preferred structure. Our better structure, and so I'll put +2 equivalent resonance structures plus our dominant structure, which doesn't put any formal charges on anything. And that's BF3. All right, let's look at BeCl2. It's also an exception, and much for the same reason that this one is. So for BeCl2, we're going to put the beryllium in the middle. All right, so there is the beryllium chloride. Let's count the valence electrons, 7, 2, and 7. So that's 14, 16. So 16 valence electrons. If everyone could have an octet, that would be 8, 8, and 8. That's 24. We don't have 24. We have 16. So that's 8, 4 bonds. And you would think, all right, well, we'll just put a double bond there and a double bond there. And when we start putting in the remaining 16 minus 8, that's 8 lone pair electrons. 1, 2, 3, 4, 5, 6, 7, 8. And you will find, if you do the formal charges, you've got +1, -2, and +1. Well, that is just not going to happen. Chlorine is not the most electronegative, but it's pretty darn electronegative. And beryllium is not very electronegative. So this is just not a very good representation of the structure. So our much more likely and the dominant structure is going to be BeCl, and we just don't put a full octet on beryllium. That means we only have 4 electrons around beryllium, but that's better than trying to put a -2 charge on that and putting a +1 on both of the chlorines. All right, so that is for beryllium chloride. So now we're going to look at PCl5. We saw PF5 on the presentation a little bit ago, but we're going to put phosphorus in the middle, and you can already see as soon as you start doing this. So phosphorus, and we got chlorine and chlorine and chlorine, and then we're like, well, where do we put that other chlorine? And we're just going to stick it right there onto the phosphorus. And so you can already tell we've broken the octet rule. We've broken the octet rule because we have 10 electrons around phosphorus. But that's okay. We can deal with that. Let's go ahead and do the math, and I'll show you how to deal with it. So 7 for each chlorine, so 7 times 5, that's 35, plus 5 more for the phosphorus, that gives us 40 valence electrons to work with. Octet, we've got 6 atoms, 6 times 8. All right, so 6 times 8 is 48. My brain left the room there for a second. So 5 times 8 is 40, and 6 times 8 is 48. Okay, so 48 minus 40 gives us 8 shared electrons. That's 4 bonds. Well, we can clearly see we've already got 5 bonds, so we're just going to take that number, cross it out, and put 5, which means that this has to be 10. So we have 10 shared electrons. 40 minus 10, that gives us 30 lone pair electrons. And if you look, we'll put 6 onto each of the 5 chlorines. 6 times 5 gives us those 30 electrons. So I'll do those real quick. Hopefully you can see all these. They're getting a little bit messy, but all right, so there it's phosphorus pentachloride. So that one has more than an octet, but it's okay because phosphorus is in period 3 on the periodic table. All right, so now we're going to look at BRF5. So we'll put that BR in the middle. And again, as soon as we start doing this, fluorine, 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 you know, that other fluorine has to go somewhere. And so it's going to go right there. All right, when we count up the valence electrons, so all 1, 2, 3, 4, 5, 6 times 7, because all 6 of these atoms are halogens, so 6 times 7 is 42. Octet is 6 times 8, that's 48. 48 minus 42 is 6, that's 3 bonds. We come over here and look, we have 1, 2, 3, 4, 5. Well, clearly, we'll change that to a 5, which means that we really used 10 shared electrons. 42 minus 10 gives us 32 lone pair electrons to put on there. And so we'll start putting them onto the fluorine. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. We've got 2 electrons remaining, and the only place we can put them is onto the bromine. Fluorine is in period 2, so cannot have an expanded octet. So that's all. We can't do that on the fluorine, but we can do it on the bromine. If we go through and look at formal charge, we'll see that all of these have a 0 formal charge. So this is the bromine pentafluoride, and that is the structure. This is a ridiculously strong fluorinating agent. Pretty crazy stuff. All right, so next we have XEF2. You can notice a lot of fluorine is involved on these. So we can already tell something's weird because we have a noble gas, and the noble gas has bonds to it, so it's already something that is unusual. So with XEF2, 7 plus 8 plus 7, So 14 plus 8 is 22. 8, 8, and 8 would give us 24. 24 minus 22 is 2. 1 bond. We already have 2 bonds. So we're going to put 2 there and change this to a 4. And then 22 minus 4 gives us 18 lone pair electrons. So we'll do 2, 4, 6, 8, 10, 12. I got a little carried away there. All right. So 12, and we have 6 more, and those 6 more are going to go onto the xenon. And you'll see that there are 10 electrons around xenon there. You'll also see that there's no formal charge. All the formal charges come out to 0 on this one. So that is xenon difluoride. So here is xenon tetrafluoride. This was the one in chapter 7. You saw a picture of that one. That one's kind of cool. But we will put XE F, F, F. All right, so there is our backbone structure. Let's see, valence electrons. So 4 times 7 is 28, plus 8 more is 36. For octet electrons, 8, 8, 8, 8, and 8. 8 times 5 is 40. 40 minus 36 is 4. That's 2 bonds. We've already got 4 bonds, so we're going to cross that out. We'll put 4, which means we've used 8 electrons. So we've used 8. 36 minus 8 is 28. And so now let's go ahead and put those 28 electrons in there. So 2, 4, 6. 6 times 4 is 24. So 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've used 24 of our 28. We've got 4 more, and those 4 more have to go on to the xenon. All right, and that is it. Okay, so that is our expanded octet. That means that we are on to our last section of the text, which is chapter 8, section 8, and it's talking about covalent bond strength and bond length, and we'll get to the bond length here in a moment. So the amount of energy that is required, that's required to break a gas phase molecule, a bond, into its atoms, right? So to break this bond into its atoms, and we're going to give 1 electron to each, that matters, okay? We call that the bond enthalpy. That's how strong that bond is. And so the bond enthalpy for a chlorine-chlorine bond, which we're going to write down as D. The D, by the way, means dissociation. So often it's talked about as the bond dissociation enthalpy. So D is 242 kilojoules per mole. So 242 kilojoules per mole. All right, so that is our bond dissociation enthalpy. Well, we've got a list of bond enthalpies that are here. These are average bond enthalpies for selected bonds, and you'll see we've got single bonds, and they're arranged by the element. So we've got some carbon bonds and silicon bonds and nitrogens and oxygen, sulfur, and then down here we've got some double bonds and triple bonds. So a couple of things you'll notice about this. One is that the double bonds are stronger than the single bonds, and the triple bonds are stronger than the double bonds. So that's kind of interesting. All right. You'll see that it is the average bond enthalpies. We'll find that the bond enthalpies are always positive values because this is the amount of energy required to break the bond. And bond breaking it's not exothermic, it's endothermic. This is supposed to say endothermic. There we go. Now it says endothermic. All right, so bond enthalpies are always positive because this is an endothermic process. So Since it's the definition is breaking a bond, then that's endothermic. Whenever we make a bond, that's exothermic. These bonds are average values, and so not every carbon-hydrogen bond is identical. And in fact, the strength of a carbon-hydrogen bond can range anywhere from, about 350 up to over 500, depending on what other stuff is attached to the carbon. So for a carbon-hydrogen bond in methane, CH4, that is going to have a bond enthalpy that's more like 435, whereas the carbon-hydrogen bond in chloroform, CHCl3, that one is more like 380 or 370. I forget the number for that one, but it's a much weaker bond. So these are average bond enthalpies, and they're just estimates. They're useful estimates. Now, when we look at the bond length and bond strength for like single, double, and triple, we will see that multiple bonds are shorter and stronger than single bonds. And a triple bond is going to be shorter and stronger than a double bond. So here you'll see carbon single, double, triple, 1.54, 1.34, 1.20. So it gets shorter and definitely stronger. You'll see the same trend here for carbon nitrogen. So shorter and stronger. Carbon oxygen single, double, triple, shorter and stronger. Over here, nitrogen, so shorter and stronger. And then single and double nitrogen, oxygen, so we get shorter and stronger. And then finally, oxygen, shorter and stronger. So multiple bonds are shorter and stronger than single bonds. I want you to know that. All right, and our last topic is calculating enthalpy of a reaction. We can estimate the enthalpy of a reaction. So anytime we break bonds, those are endothermic, and anytime we make bonds, those are exothermic. So if we want to calculate the bond enthalpy, we're going to get the sum of all the bonds that are broken and subtract the sum of all the bonds that are formed. And we're going to use this rather simple formula. So the delta H of reaction should be equal to, at least a good estimate should be equal to, the sum of all the enthalpies of the bonds that are broken minus the sum of all the enthalpies of the bonds that are formed. And that's it. So as an example of this, we want to look at this particular reaction. So here we have methane reacting with chlorine to give us chloromethane and HCl. Okay, well, the bonds that are broken, we're going to break a carbon-hydrogen bond here and the chlorine-chlorine bond. And then over here, the bonds that are formed are going to be the carbon-chlorine bond and the hydrogen-chlorine bond. So the way that we'll do this is that we're going to add up all the bonds that are broken. So the enthalpy of a carbon-hydrogen, the enthalpy of a chlorine-chlorine, all right. And then over here, we're going to have the enthalpy of a carbon-chlorine plus the enthalpy of the hydrogen-chlorine. All right, I had to fix those brackets real quick. That was driving me crazy. All right, so, and then if we just go to the table and look up these values, go to the tables and look up these values. And when we do that, we're going to get 413 for the carbon-hydrogen, 242. We just saw that one a little bit ago. The carbon-chlorine, 328. And the hydrogen-chlorine, 431. And then finally, we'll get the subtotal, and then we get negative 104. So the use of this is, one, it tells us if a reaction is going to be endothermic or exothermic. And we saw earlier in chapter 5 that exothermic reactions tend to be more favorable. When it comes to thermodynamics, that we're just more likely to have a reaction work if it is exothermic. And so knowing that this reaction is exothermic, it's going to make it much more likely that we can make that reaction work. All right, and we're going to do, it's actually 8.65, but that's okay. let's do this. All right, so use the bond enthalpies in table 8.4 and then estimate delta H for each of the following gas phase reactions. So we want to look at the bonds that we break and the bonds that we formed. So the bonds that we break here, going from here to here, is that we're breaking that carbon-carbon double bond. Now, really, we're just breaking one of the bonds, but it's easier just to break both of them and then make a carbon-carbon single bond over here. We're also breaking that oxygen-oxygen single bond. And then the bonds that we're going to form are carbon-oxygen single, carbon-carbon single, and carbon-oxygen single. So I would write this as delta H is equal to the enthalpy of a carbon-carbon double plus a oxygen-oxygen single, and then the bonds that are formed is going to be 2 times the enthalpy of a carbon-oxygen single plus the enthalpy of a carbon-carbon single. And now we just need to look up the values for these on that table. All right, so here we go. I've got these right here. So the carbon-carbon double is worth 614. And the oxygen-oxygen single is up there at the top, and it is worth 146. And then we've got 2 times the carbon-oxygen single, and you'll see here it is worth 358 plus the carbon-carbon single, and it's worth 348. Okay, so now that we've got those numbers, clear all that. Okay, so 614 plus 146. That gives us 760. And then minus, we'll do 2 times 358 plus 348. And that's 1064. All right, and then we'll just go up and grab those numbers. So that minus that, and that gives us negative 304 kilojoules. So that tells us that that reaction is pretty exothermic. So pretty exothermic. All right, this one's a little trickier because we're breaking a carbon-hydrogen bond and we're making a carbon-hydrogen bond. And sometimes that can be a little bit confusing, but kind of look at it is that this is going here and that carbon is going there. So we're going to break that carbon-carbon double bond, and we're going to break the carbon-hydrogen single bond, and we're going to make a carbon-hydrogen single, a carbon-carbon double, or carbon-carbon single, and another carbon-carbon single. All right, so delta H is going to be equal to the enthalpy of a carbon-carbon double plus the enthalpy of a carbon-hydrogen single. And then we're going to subtract the enthalpy of a carbon-hydrogen single plus 2 times the enthalpy of a carbon-carbon single. All right, and we'll look up those numbers. So here, this is going to be, this one's still 614. I'll go back to that right there. The carbon-hydrogen is worth 413. All right. right, and then this carbon hydrogen is also worth 413 plus 2 times the carbon-carbon, and that carbon-carbon single is worth 348. All right, so go back to this. We'll clear that. We'll do 614 plus 413. That gives us 1027 minus, so 413 plus 2 times 348. That gives us 1109. And then I'll just go up and grab that. So 1027 minus 1109, and that gives us negative 82 kilojoules. All right, so these numbers are not going to be perfect. They're really just estimates because of the things that we talked about a little bit earlier. All right, let's draw these molecules out. So we've got methane and oxygen. And that's a 2 in front, so we're going to break all those bonds. Or not break all of them, we're going to make 2 of those. All right, so when we look at the bonds that we break, we're going to break 2 times the carbon-hydrogen, and we're going to break that oxygen-oxygen double bond, and we're going to make 2 times the carbon-oxygen and 2 times the oxygen-hydrogen. All right, so delta H is equal to 2 times the carbon-hydrogen plus the oxygen-oxygen. And the bonds that are formed, we've got a carbon-oxygen, so 2 times the carbon-oxygen and 2 times the oxygen-hydrogen. And we'll just have to go look up those values. All right. So 2 times, that one is 413. And then the oxygen, it is right here. It's that 495. And then 2, the carbon oxygen is 358. Plus 2. And the OH is worth 463. That one's pretty strong. Okay, so let's do these subtotals. So 2 times 413 plus 495, and that gives us 1321. And then we'll do 2 times 358 plus 2 times 463. 1642. So 1642. And then we'll just go and grab those. So that minus that. And that gives us negative 321 kilojoules. All right. Well, that is the end of that, I think. Making sure there's nothing else. My favorite page in every chapter, which is this page. All right, so that is the end of that is the end of chapter 8. So stay tuned for chapter 9.